A very good morning to Anjay Hamza. My name is Oman Kate. I am from BMKM. My matrix number is B0922102003. So our topic for our assessment today is about the chemical reactor. So I would like to start with the introductions of the chemical reactor. So chemical reactor is a key component in chemical manufacturing. It is responsible for converting raw materials into desired products through controlled chemical reactions. So there are several common types of reactors, including batch reactors, plug flow reactors, continuous stirred tank reactors, and packed bed reactors. So the choice depends on factors like reaction types, heat and mass transfer needs, and desired production rates. So each reactor system includes key components such as a corrosion-resistant vessel, inlet and outlet lines for reactants and products, temperature control systems like jacket or internal coils, and mixing device such as uh, agitators or catalyzed beds depending on the reactor types. So the reactor is critical for managing reaction kinetics, conversion efficiencies, product selectivity, and overall safety. Ultimately, a well-designed reactors help enhance process performance, reduce energy consumptions, and ensure consistent product quality. Next, I would like to continue with the process analysis and model development. So, the modeling begins with two fundamental aspects, mass balance and energy balance. First, the material or mass balance help us track how the concentration of each chemical species change over time or along the length of the reactor. This depends on whether the reactor is operated in batch mode or as a continuous process. Next, the energy balance considers the heat produced or absorbed during the chemical reactions. This is especially important in exothermic and endothermic systems, where the temperature control directly affects reaction rate and safety. So together, this balance form the foundations of reactor modeling, allowing engineers to predict behavior, design better systems, and optimize performance. To develop accurate dynamics or steady-state models of a chemical reactor, we need to incorporate reaction kinetics, also known as rate laws. These describe how fast a reaction occurs and are typically derived from the experimental results or literature data. In addition, we use process identification techniques such as step response and pulse testing to gather real-time data from the system. These techniques help us understand how the systems react to change and allows us to estimate important model parameters like time constants, gains, and delay. By combining kinetics with process data, we can create reliable models that are essentials for control designs, optimizations, and troubleshooting in chemical process systems. So, once we have built a model, the next step is to validate it using simulation tools. So, the tools that are commonly used is MATLAB or Simulink for dynamic system simulations, Aspen HYSYS, which is widely used in process industries, and ChemCade for chemical process simulations and designs. So this platform allow us to test how the model behaves under different operating conditions. In reactor modeling, the key variables we monitored include temperature, pressure, concentrations, and flow rates. For instance, increasing the temperature can speed up the reaction rate, but it can also reduce the selectivity or trigger unwanted side reactions. So there is always a trade-off. That's why accurate modeling is essential, not only for predicting reactor behavior, but also optimizing performance and designing effective control system.
Assalamualaikum. I'm Sharifah Paseha Adila binti Mazam Shah, metric number B0922105557. Today, let's quickly cover why pressure safety system in our chemical reactor are absolutely essential. We look at it from three angles: safety, legal requirements, and protecting our environment. To begin with, safety first. Our reactors deal with high pressure and temperature. If this get out of control, things can go very wrong, like an explosion, fire, or toxic gas leak. Our safety systems, such as pressure relief valves, act as our frontline defense. They automatically release excess pressure to prevent these dangerous situations. We also control temperature very carefully, as a sudden rise can cause rapid pressure increases. So our system have emergency shutdowns to keep everyone and everything safe. Next, legal compliance. Installing this safety system isn't optional, it's a legal must. We follow strict national and international rules like those from ASME, API, and OSHA. These rules cover everything from how we design and install this system to how we operate and maintain them. They also dictate how we handle any emissions, even in an emergency, to protect both people and the environment. Not following this rule can lead to big fines, legal problems, and even shutting down our operations. It's simply not something we can ignore. Finally, environmental stewardship. If a safety system needs to release pressure, the material could be harmful to the environment. That's why our system includes ways to manage these materials responsibly. This often means sending gases to flares to burn them off, using scrubbers to clean them, or having containment systems to prevent them from going into the air or water. We also work hard to minimize everyday leaks, called fugitive emissions, through good seals and detections. Our clear goal here is to protect our air and water quality. In short, strong pressure safety systems are absolutely vital. They are how we guarantee protecting lives, following the law, and safeguarding our planet. After discussing why pressure safety systems are so vital for safety, legal, and environmental reasons, let's look at what exactly we need to control inside a chemical reactor. Our main goal is always to run things safely, efficiently, and with good quality. To do this, we focus on managing a few key things. First, temperature. This is super important because it controls how fast our chemical reaction happens. If the temperature gets too high, the reaction can speed up dangerously, causing pressure to spike and potentially damaging the reactor itself. So we keep a very tight watch on temperature to stay safe and make the right product. Next, pressure. This is directly linked to our safety system. Our top priority is to make sure the reactor's internal pressure never goes above its maximum allowable working pressure, or MAWP. Too much pressure can cause the reactor to burst. Our control system constantly monitors this, and if pressure rises, they either fix it or activate our safety relief valve. Then we have flow. This is about how much stuff goes into and out of the reactor. We control the flow of reactants to make sure the chemistry is just right. We also manage the flow of coolants to remove heat, which is essential to prevent temperatures and pressures from getting too high. And we might use inert gases to purge or maintain pressure, all contributing to a stable process. Level is also key, especially for liquid-filled reactors. Keeping the liquid at the right level ensures good mixing and heat transfer. If the level is too high, there isn't enough space for pressure to build up safely, which is dangerous. If it's too low, we might not cool effectively, or it could even damage part of the reactor. Finally, there's composition. While we don't always directly measure this, knowing what's inside the reactor is crucial. Wrong ingredients or impurities can change how the reaction behaves, affecting heat and pressure. We monitor other factors to make sure the chemical mix is safe and correct. So, by carefully controlling these main variables, temperature, pressure, flow, level, and composition, we keep our reactors running safely, efficiently, and produce the quality product we need.
Assalamualaikum. My name is Sharizan bin Bahri. Number matrix B09 2210 317. This is about control system variables. First is manipulated variables. Operating pressure relief valve. Engaging the emergency venting system. Adjusting the coolant flow rate through the reactor jacket. Number 2 is disturbance variables. Variations in feed composition or feed flow rates. Unanticipated reaction responses, such as thermal runaway. Variation is ambient temperature that affect heat exchange. Number 3 is controlled variables. Reactor internal pressure, reactor temperature, venting flow rate, and liquid level in the reactor to avoid overflow. Now, continue about control structure selection. First is interacting variables. In the chemical reactor system being controlled, there are significant variable interaction as several parameters: pressure, temperature, and flow. Number 2 is a multi-variable, MIMO multiple input, multiple output. Control system can manage the coordinate, the control multiple interacting variable at the same time.
Bismillahirrahmanirrahim. My name is Rajan Makmur and I will present about the instrument that include in chemical reactor. Instrumentation play a vital role in ensuring the safety operation, efficiency and accurate control, particularly when integrated with a pressure safety system. There is some types of primary measure required, which includes temperature, pressure, level, and flow measurement. So next slide, development of an effective control system for a chemical reactor. Phase 1 will be dealing with studying academic and industrial standard in reactor control and safety, and focusing on feedback and feed-forward control strategy. The second phase, process modeling development, develop a dynamic model using MATLAB, incorporated mass and energy balance, simulate normal and upset condition to define safety limits. Then the third phase is control strategy selection. Consider model predictive control for proactive adjustment aimed at enhancing response to temperature, pressure, and flow variant. And the fourth phase is implementation. Selected and install field instrument and controller. Configure safety interlock. For the conclusion, through this assignment, the importance accurately understand the reactor system from equipment design and process modeling to safety, legal, and environmental consideration has been highlighted. Key control variables such as temperature, pressure, flow, level, and composition must be carefully monitored and managed to prevent hazardous scenarios, especially under high pressure and high temperature conditions.